Hi, I'm Okamura from Japan, and I'm conducting research at Kyushu Institute of Technology. And I'd like to talk to you about improved method of preparation for shape memory polymer sheet with embedded electrical heating wire for use in pneumatic artificial rubber muscle.
As you might already know, meanwhile, the birth rate is declining and the population is aging significantly in Japan. We are facing a severe shortage of caregivers nowadays. Due to this circumstance, robotics technology is being significantly introduced into the fields of nursing care and welfare. In addition to that, many situations in which humans and robots are in direct contact are assumed in this field. That's why the feature these robots need to have is flexibility, like PowerShift Grab has. Considering these things, we've been working on development of artificial rubber muscle using shape memory polymer. That is called SMP. Anyway, let me explain about artificial rubber muscle using SMP. So let me begin by explaining the feature of SMP first. As shown in this graph, when the SMP is heated above Tc, its elastic modulus changes to 0.1 to 1% of that below Tc. So using this feature, we fabricated SMP seats with embedded electrical heating wire that can arbitrarily control temperature changes. And then we attach these seats on the both sides of the artificial rubber muscle in order to control the behavior of it. Anyway, I want you to watch this video. So by heating only one side of the seats, and when an internal pressure is applied to an artificial rubber muscle, it can be controlled in arbitrary direction, like this. So this allows for both the flexibility of conventional artificial rubber muscle, as well as much degree of freedom. However, unfortunately, conventional SMP seat had problems in its fabrication process and structure. The first problem lies in uneven spacing of electrical heating wires. The heating wire was manually bent along a molded channel, produced by a 3D printer into the shape. That's why it can be seen that the embedded electrical heating wires were not evenly spaced. Another lies in improper shape of electrical heating wires. As you can see, the ratio of cross-sectional area of the electrical heating wire to that of the SMP differed depending on the position in the seat. And the SMP seat sometimes broke apart when the SMP ratio was small. In order to solve these problems, we set a goal as improved method of preparation for shape memory polymer sheet with embedded electrical heating wire. So the first is to improve the fabrication process of electrical heating wire to improve reproducibility. The second is to change the shape of electrical heating wire and make the ratio of electrical heating wire to SMP uniform. So simply put, we decided to fabricate a new type of SMP seat, and after that, we also conducted several experiments to compare the performance of previous and new SMP seats. So here's SMP fabrication process. First, liquid A and B were stirred in the flowing cycle using the machine shown here. And after that, the stirred SMP was heated and cured in a vacuum for at least 4 hours. And finally, the cured SMP was heated and pressed to the desired thickness. That was 0.4 millimeter in this time. And the catalog values of SMP is here. Actually, this is one of the most important slides in this presentation. So here's electrical heating wire fabrication process of new SMP seat. So first of all, we drew electrical heating wire into the cathode. And as you can see, by placing wire diagonally, its cross-sectional area was constant over the entire length of SMP seat. So we found that the ratio of SMP to electrical heating wire became uniform. In addition, nitron foil was used instead of nitron wire in order to enable machining using a computer pneumatically controlled engraving machine. Changes in this process could improve reproducibility. And then here's the electrical heating wire after cutting. So this is comparison of samples 1 and 2. I'm going to call sample 1 as new type and sample 2 as previous type. Visual inspection shows that the spacing of electrical heating wires in sample 1 is more uniform than sample 2. And here's an image of each seed when heated. It can be seen that the temperature distribution of sample 1 is more uniform than that of sample 2. And based on these results, we found that the fabrication process for SMP seeds with embedded electrical heating wire was successfully improved.
Here is experiment 1 in order to compare the mechanical properties of two SMP seeds. In bending test, one side of SMP seed was fixed to an automatic stage, and we pressed it against the roll cell to measure the elastic modulus. And when it comes to tensile elastic modulus, it was measured by fixing each end of seed to a roll cell and an automatic stage and pulling. Measurement conditions for both of them are here.
And we used linear pneumatic artificial rubber muscle that was developed in our previous study. And then we attached each seed to the artificial rubber muscle to check their behavior. Here's experiment 2 in order to evaluate the behavior of artificial rubber muscle with the SMP seeds attached. In isometric test, the force is measured when the artificial rubber muscle pushes the roll cell. And actually, isometric test is one of the most commonly used methods for evaluating artificial muscle. In bending test, the angle of bending of the artificial rubber muscle was measured by tracking the red tape that was attached around here. And we used the previous data for sample 2. And the measurement conditions for both of them are here. So this is experimental result of bending test, and the vertical axis of this graph shows elastic modulus, and horizontal axis shows the velocity. And I'd like to draw your attention to the elastic modulus below TG first. As you can see, they were similar to catalog values. And when it comes to the elastic modulus above TG, then they differ from the catalog values, though their respective values were really close. So these results confirm that the elastic modulus of samples 1 and 2 were equivalent. This is experimental result of tensile test of road capacity. And the vertical axis, this graph shows the force, and the horizontal axis shows the displacement. And I'd like to draw your attention to this yellow line first. According to the previous study, when an internal pressure of 0.1 megapascal was applied to an artificial rubber muscle, the extension force was generated was around 14 Newton. And you can see that both samples 1 and 2 were confirmed to be able to withstand 100 Newton load with no rupture. So from these results, we found that the durability of samples 1 and 2 were equivalent. This is experimental result of tensile test about tensile elastic modulus, and the vertical axis of this graph show the elastic modulus, and the horizontal axis show the velocity. I'd like to draw your attention to the tensile elastic modulus below TG first. Due to slippage of the seed fixing part, the tensile elastic modulus was a bit smaller than catalog value though. The result for each seed were really close. However, when it comes to the tensile elastic modulus above TG, then it can be seen that the tensile elastic modulus of sample 1 was obviously larger than sample 2, and we assume that this is due to the change from nylon wire to foil, which increases the longitudinal modulus of elasticity and makes it more difficult to stretch. So based on this result, we found that tensile elastic modulus of samples 1 and 2 were not equivalent. This is experimental result of isometric test. And the vertical axis of this graph show the maximum force, and the horizontal axis show the bending angle. And first, I'd like to draw your attention to the comparison of each sample. As you can see, the generated force for sample 1 was lower than sample 2. And this result was also attributed to the change from nylon wire to foil, which increased the tensile elastic modulus. In addition, Similar to the results of the previous study, both samples showed a decrease in force after the bending compared to the force before the bending. This is the experimental result of bending angle measurement, and the vertical axis, this graph, shows the bending angle, and the horizontal axis shows the pressure, and we used the previous data for sample 2. When it comes to the maximum bending angle of sample 2, it was 9.6 degrees, and when it comes to sample 1, that was 3.0 degrees. So, as this result was also attributed to the change from nylon wire to foil, which increased the tensile elastic modulus. And consequently, as well as the result of isometric test, we found that the bending angle of sample 1 was smaller than sample 2. Anyway, let me summarize the key points today's talk. So from all experimental results, we have confirmed that we have successfully improved fabrication process for SMPCs with embedded electrical heating wire. However, unfortunately, we also found that performance degradation as artificial muscle. That's why we are currently working on an initiative to balance improved reproducibility and performance as artificial muscle. For instance, we tried to change the shape of the seed and the metal used for electric heating wire. That's it. Thank you for your attention.